Good evening, everyone. My name is Ela Siwek. I'm a member of the Engineers Island West Region Committee. This webinar is a part of the Engineering National Development Series organized by the West Region. The series marked the recent publication of Ireland's National Development Plan 2021-2030 and promote new ideas for engineering practices across all sectors aligned with the Project Island 2040 strategy. Under this session, we are delivering two events linked together and titled Transforming Our Water Supplies for Your Future. The talk last week, part one, was called Strategy and Planning. We invited two excellent speakers from Irish Water to this talk, Miriam Grant from Water Asset Strategy, who has been involved in the preparation and programming of the National Water Resources Plan, and Des Joyce, who is currently the water supply lead for Irish Water's asset planning section. The National Water Resources Plan is Irish Water's 25-year strategic plan for Ireland's public water supplies. The plan allows us to move towards a safe, secure, reliable, and sustainable drinking water supply for all Irish water customers while safeguarding the natural environment. Groundwater resources are important to Irish Water, currently providing 17% of total supply by volume. The first presentation provided an understanding of the development of the Irish Water 25-year strategy for drinking water supplies in Ireland and explained how Irish Water will address immediate and critical needs across these water supplies over the next 5 to 10 years. This evening's talk is part two, called Groundwater Resources Assessment, and it will focus on a few examples related to the Irish Water Strategy. I'm delighted to have here today two fantastic speakers from TOBIN Consulting Engineers, Joe Greene and Darren Clark, both from the Environment and Planning team. Our first speaker tonight is Joe Greene. Joe holds the position of Project Hydrogeologist with TOBIN's Environment and Planning section. Since graduating from the University of Birmingham in 2016 with a master's degree in hydrogeology, he has worked in consultancies in the UK and Ireland, focusing primarily on groundwater resources. Joe has extensive experience in the delineation of source protection zones, zones of contribution, reviewing, processing, and quality assuring large hydrometric monitoring datasets, Warhol drilling, as well as the supervision and reporting of groundwater sampling and analysis. Since joining TOBIN in 2019, Joe has contributed to a variety of projects, including the assessment of regional groundwater potential for the exploration and development of new groundwater resources, the remediation and development of existing groundwater sources around Ireland, and the development of source protection plans for public water supplies. Joe will deliver a talk on the GSI Groundwater 3D regional assessment of potential groundwater resources, focusing initially on 32 catchments in the east of Ireland. These assessments develop an initial hydrogeological conceptual model for the catchments and provide a basis for prioritizing further investigation into groundwater resources. The talk will discuss the methodology which underpins the assessments using the catchment in the east of Ireland as an example. Our second speaker this evening is Darren Clark. Darren holds the position of project hydrogeologist within TOBIN's Environment and Planning division as well. After completing his master's degree in hydrogeology at the University of Strathclyde in 2017, he spent a number of years working for a consultancy in the UK. During this time, he provided technical support and task leadership on a wide range of water resource projects, focusing primarily on the delineation of source protection zones, hydrometric monitoring, sampling, and technical report writing, Warhol drilling, as well as providing technical support to a number of quarry-related projects across the UK, including the development of hydrogeological environmental impact assessments to form a part of environmental impact assessments report. Since joining TOBIN in 2020, Darren has been working with the Irish Water on their National Water Resources Plan as a groundwater resource planner. This role mainly involves a desk-based assessment of many of Ireland's existing water supplies, in addition to assessing the potential of for the exploration and development of new groundwater resources. For the purposes of the framework plan, a simple methodology has been developed for assessing the hydrological yield of groundwater sites. The talk will use a couple of case studies to help explain the methodology used, which takes into account a number of factors from risk to contamination, flooding, aquifer classification, and the concept of recharge and zones of contribution. At the end of these two presentations, we will have a Q&A session. So please ask your questions in the Q&A box at the bottom of the screen and not in the chat box. So we will start with the presentation now. Joe, please, you can start.
Thanks, Milanila. So thank you everybody for taking the time out of your evening to dial into my talk. I promise that Darren and I will be wrapped up before Champions League kickoff later on. My name is Joe Greene and I work for TOBIN Consulting Engineers, and for the past couple of years or so I've been working on the Geological Survey of Ireland's Groundwater 3D project, contributing to a series of reports which assess regional groundwater resource potential on a number of catchments in the east of the country. So my talk will focus on the broader catchment scale of groundwater resource assessment, whereas Darren Clark, who will be talking after me, will focus on assessing groundwater resources at a smaller, more localized site scale. So I'd like to start by firstly introducing the Geological Survey, more commonly known as the GSI. It's in its most simple terms possible, the GSI is Ireland's public earth science knowledge centre. It is a division of the Department of the Environment, Climate and Communications. And its commitment to Ireland is to provide free, open and accurate data and maps on Ireland's subsurface to all parties who may be interested in the data. And they also often act as project partners and offer their expertise towards interpreting data and developing models and data viewers to help people understand the underground of our country. So on to the Groundwater 3D project. So the project focuses on catchment-based assessments for groundwater resources. And the aim of the project is to identify high potential groundwater resources which could be exploited for long-term sustainable groundwater drinking water supplies. Long-term and sustainable being the key word so far, especially in the context of growing population and climate change and other strains which Ireland will experience in the future. The project was initiated with Irish Water and focuses on public water supplies. The project works closely with the EPA and incorporates much of their data and bears in mind their future environmental objectives. The initial focus of the project is on these 32 counties in the east of the country. These were chosen as there have been supply-demand deficits forecast in this region, Dublin City being bang in the centre of it. Now I'm conscious that I'm talking about a project in the east of the country to Engineers Ireland West, but the ambition of the GSI is to eventually roll out this methodology to as many catchments in Ireland as possible. So just a bit more on why the project was started. I think we're all aware, more so now than ever, of the growing strain being exerted on Ireland's drinking water. Generally speaking, we're experiencing more volatile winters and drier summers, and there's a greater polarity of the seasons. And since the bad drought in 2018, which you can see here, we saw the implementation of the first hosepipe ban in Ireland. Droughty periods have been a constant fear. And given the nature of Ireland's environment, when things are dry for an extended period, water can be hard found. And groundwater can help somewhat in this regard, as there can be a lag time between the response of groundwater to antecedent weather conditions. You can see there, as recent as 2020, started dipping into some scary droughty figures. There were 7 public water supplies categorized as in severe drought, 30 in drought, and a further 59 in potential drought, and this all affected nearly 1 million people. So onto the Groundwater 3D project. So we've developed a general approach this four-step approach, which can be applied to most any catchment in Ireland. So the first step is to identify the groundwater resources within each catchment. I'll show you an example of how we do this shortly. But the end result is that we can break up the catchment into more discrete hydrogeological conceptual zones. And we can then pluck out the zones which we believe have higher regional groundwater resource potential. And we then move on to step number 2, which is where we scrutinize each of these zones which we have identified for possible limitations to any future groundwater abstractions. And I'll show you what I mean by limitations shortly. And once we have these 2 steps completed, we can then compare the higher priority zones across all of the catchments and create a list which can be prioritized based on their groundwater resource potential. And then we can move on to this final step, and we're currently transitioning into this step now. And we can use this list of prioritized sites to decide where best to focus our field work to verify and quantify those resources. So we want to ground truth everything that resulted from our desk-based work. And the outputs of the project are going to be a report for each catchment. This is the front cover of the Barrow catchment, and the whole report series will have a cover series similar to this. The other output is this prioritized list of groundwater resources, which can be picked up by pretty much anybody. And then eventually field verification of the most promising resources. So we're focusing on groundwater resources by using surface water catchments, and it's a fair question to ask why. Well, there are a number of rationales for this. Firstly, surface water catchments are the internationally recognized unit, or they are an internationally recognized unit, and they can be a more simple concept to understand. Unfortunately, it's sometimes the case that groundwater is out of sight and out of mind. Secondly, it's becoming more and more important to consider the whole hydrological and hydrogeological system as an integrated system. In order to fully understand one part of the system, you really need to understand the system as a whole. Thirdly, by basing our catchment assessments on these surface water catchments, we can deploy a water balance, as we have generally a closed loop water cycle. So a water balance is a relatively simple tool where input should equals output. So the inputs are the likes of rainfall, anthropogenic discharges, all of the input of water into the system. And we can compare these to a measured output at the terminus of the surface water body. So if we have a gauge at the terminus of that river, we can compare the input to the output. If we don't, we can model that point. And if there's a discrepancy between those 2 points, we can start to investigate why there may be a data gap in our desk-based study that we need to find. So back onto our groundwater 3D approach. So firstly, we identify the groundwater resources within each catchment, and we do so by looking at all of the available data for that catchment. And at this stage, we're really trying to conceptualize the catchment. And this involves taking into account all of the physical properties of the catchment, such as soils, subsoils, bedrock, aquifer types, meteorological data, such as rainfall, evapotranspiration. We look at groundwater recharge. We look at hydrometric data in the form of surface water flows, groundwater levels. We look at available surface water and groundwater chemistry data. We look at everything we can get our hands in order to create a picture, as whole a picture as we can of the catchment. So I'm going to show you how we might do that. I'm going to use the Slaney catchment as an example. It's a fairly well-known catchment, so I chose it. It's down in the southeast of the country. It covers an area of about 1,750 kilometers squared. Has a population of approximately 100,000 people. Spans 3 counties, so straddles Wicklow, Carlow, and Wexford. And the main town is Enniscorthy down here to the south of the catchment. So when we are conceptualizing our catchment, we generally work from the uppermost layers and move down through the stratigraphy. And I've put a nifty little stratigraphy chart here to help us keep our bearings as we move through the maps. So it can be a bit of a bombardment of maps. The first thing we look at in the uppermost layer is the topography. So in the northeast of the catchment, we have the Wicklow Mountains. To the west of the catchment, we have the Blackstairs Mountains, and then there's this elevated region in between them. And the surface water network is largely a factor of that topography. So this north-south trending channel here is the Slaney River, which flows in the valley between these two elevated regions. And then there are some major tributaries which flow from the elevated regions and join the Slaney along its journey. Moving down through the stratigraphy into the soils and subsoils, the Slaney is largely characterized by tills from various parent rocks. So these pinky into purple colors represent till. There's a lot of outcrop and subcrop, particularly in the elevated areas, and these are represented by these gray polygons. And then the greens represent sands and gravels, generally concentrated along the main Slaney river channel. And some of these sand and gravel deposits are categorized as locally important sand and gravel aquifers. So looking at the soils from the subsoils from a permeability perspective, and this is important when you can think of it from groundwater resources perspective, because subsoil permeability is important as it dictates the ease with which rainfall can reach the bedrock. For the most part, where the tills are present, we have moderate permeability. It is high where the sands and gravels are present. There's a lot of gray polygon, and that's where soils are very thin to non-existent, generally concentrated up here in the upland regions. And then we have this area to the east of Enniscorthy where we have low permeability subsoils. And the subsoil permeability is reflected in the Groundwater Vulnerability Map, where the highest groundwater vulnerability occurs where bedrock is at the surface. So again, up in these elevated areas, there's little to no soil cover to protect the groundwater aquifers. And these areas kind of transition into high to moderate vulnerability where the moderately permeable tills are present. And then we have this area of lowest groundwater vulnerability occurring where those low permeability tills are present to the east of and south of Enniscorthy. Moving down through the stratigraphy again, we're in the bedrock, and there are quite a number of individual bedrock formations in the Slaney catchment. It can be hard to kind of get your head wrapped around these. But these can be grouped based on their hydrogeological properties and other factors into these rock unit groups. And it's just a bit easier for your brain to kind of comprehend it. So the red color pops out, and that's these are granites and other igneous intrusive rocks. The purple polygons represent Ordovician metasediments, but this unit here represents Ordovician volcanics. And these Ordovician volcanics become quite significant when you look at the bedrock in terms of aquifer classification. So this is the Aquifer Map. And for the most part, the bedrock in the Slaney catchment is characterized as poorly productive aquifer, certainly in terms of regional groundwater resources. So these brown colors represent poorly productive aquifers, and this area to the south also. However, this band of green represents those Ordovician volcanics, and these are characterized as regionally important aquifer. And this is by virtue of a large degree of fracturing and fissuring, which creates flow paths that are much greater than those which might be found in these poorly productive aquifers. So we're kind of onto something in terms of regional groundwater resource potential when we're looking at this. Looking at the groundwater recharge, you can see that recharge is highest. So the brighter the green, the greater the recharge. It's highest on in the area of these Ordovician volcanics, perhaps excluding the area east of Enniscorthy, if you recall from a couple of slides earlier, where the low permeability subsoils are present. So that's a very quick run through the physical section of the Slaney. But once we have compiled all of that data together, we can then start to break the Slaney into more discrete hydrogeological conceptual zones. We can pluck out the zones then of higher groundwater resource potential. So here we have 4 zones. Zone A is this large purple polygon here, and that's characterized by the poorly productive, in terms of regional groundwater potential, aquifer. Looking at this figure here, you can see that only 22% of the effective rainfall is recharging the groundwater system. So you're running into concerns over long-term sustainability. Abstraction might not get enough recharge if you were to cite it here. Similar case down here in this zone D. However, in zone B, for example, where our Ordovician volcanics are located, we have a much higher percentage of effective rainfall recharging the groundwater system. So we have a groundwater dominated area. And it's areas like this that we're interested in. And once we have picked out areas like this, we can then move on to step 2 of our methodology, which is to scrutinize the preferred zones for potential limitations to future abstractions should we cite them in these zones. And there are 5 potential limitations that we are concerned about. We're concerned about hydrogeological limitations. So these are physical limitations to the long-term sustainability of any potential abstractions. We look at ecological limitations. There might be some protected habitat within the zone, and we don't want to be affecting those. We look at other abstractions. We don't want to be competing directly with existing abstractions. We look at the chemistry. So are there any natural or anthropogenic chemistry issues which might limit the future or even the current viability of an abstraction? And we also look at climate change, how climate change might impact the future viability of an abstraction. So just to give you an example of how we might examine potential limitations in this zone, zone B, the Ordovician volcanics. We'll start with the whole recommended zone as a bit of a blank canvas, and we'll apply the limitations and see what we're left with at the end. So starting with potential hydrogeological limitations, we screen out generally areas of poorly productive aquifer and low recharge, and we consider areas of under 100 millimeters of recharge per year as low recharge. And our concern is that areas of low recharge would impact the long-term sustainability of a future abstraction. So in this case, we have quite a lot of recharge here to the southwest of Enniscorthy, but up here to the northeast, we have these areas of what we consider to be low recharge, and we screen out these areas. Again, we're concerned that these areas might have long-term sustainability issue. We then look at potential ecological limitations in the form of protected habitat predominantly, and we pay particular attention to habitat which might be sensitive to groundwater abstractions, such as groundwater dependent terrestrial ecosystems and the likes. So in this case of the Slaney, we have this very large special area of conservation, the Slaney Valley SAC. However, there are no features in this SAC that are particularly sensitive to groundwater abstraction. There are certain features such as fen and that, which are very sensitive to even the slightest drop of the groundwater or the water table. But just so we bear it in mind when we're looking at the zone, we screen it out. Looking at other abstractions. So let's first talk about these purple blobs. These are zones of contribution to groundwater abstractions, which Darren will talk about in a bit more detail in his talk. But we want to screen out these areas as we want to avoid competing directly with existing abstractions. For the remainder of the abstractions, the surface water and groundwater abstractions, we conduct an abstraction impact assessment. And this involves two tests. The first test assesses the impact of groundwater abstractions as a percentage of the overall groundwater recharge. The second test assesses the impact of surface water abstractions and discharges on the surface water flows. And these will be examined further in the near future by the EPA as part of the Water Environment Abstractions Bill, which I'll talk about in a moment. But without getting bogged down in too much detail, there are certain thresholds which can't be breached in terms of how much water we can remove from the system. And if we find that abstractions are proportionally high in a zone, it is definitely something that will need to be considered in terms of potential future abstractions. There might not be room for further development of abstractions in that area. So a bit more about the legislation. To date, there's fairly limited legislation on water abstraction in Ireland. However, this is changing. In 2018, there was a requirement brought in for whoever abstracts more than 25 cubic meters of water per day to register their abstraction with the EPA. And this is a requirement of the Water Framework Directive. And then coming down the line shortly in the near future is this Water Environment Abstraction Bill, which stipulates how abstractions will be regulated. And this is currently undergoing pre-legislative scrutiny. The legislation is expected to drop at some point this year, maybe early next year. And this bill requires a cumulative and quantitative assessment of the environmental impact of abstractions, and these assessments will largely be carried out by the EPA. So we also look at the chemistry. In terms of this Slaney Zone B, there's not that much groundwater chemistry data available. There are two observation points in Zone B. There's the Enniscorthy water supply and the Edermine water supply. And the primary issue at these points is elevated nitrate. So the average concentration at these 2 points is 36 milligrams per liter. We know in general that in the southeast of the country that nitrate is high, and in some areas it is approaching and occasionally breaching the drinking water threshold of 50 milligrams per liter. And in a broader context, and Des touched on this in his talk last week, untreated water chemistry in Ireland can vary a fair deal in time and space, but there are a suite of common issues which should definitely be investigated for when considering a future abstraction, such as iron, manganese, nitrate, that sort of thing. But it is important to get a handle on how potentially problematic chemical parameters are trending and considering the viability of a future water abstraction. We then need to consider climate change and how this might impact future abstractions. We are currently relying on the study from Broderick and Murphy, and it effectively gives an assessment aimed to gain a better understanding of how river flows may change as a response to climate change. And they evaluated 206 river catchments in Ireland and categorized these into 5 catchment types. And here they are, the 5 catchment types. Without getting into too much detail here, Slaney falls into type A and type D. And these are less sensitive to seasonality and more sensitive to changes in the annual mean precipitation. And they are characterized by this greater residence time, so kind of greater natural storage. The other thing we need to be to bear in mind will be the modeled reduction to the Q95 flows. So the Q95 flows is the flow that has exceeded 95% of the time. So it's a typical dry summer flow. And in the Slaney, the model predicts a reduction of anywhere between 4 and 21% in Q95 surface water flows by 2080. Just while we're here, in the west of the country, tends to fall into the type C or type E category. So where we started with this blank recommended area, after applying our potential limitations, we have a much better idea now of where to focus our efforts and kind of where to avoid. And this is just an example of one recommended area. We're nearly to the point where we have the recommended areas picked out from all of the catchments and studied for limitations. And we're beginning to combine all of the results together between all of the catchments and beginning to get an idea of where to prioritize for further investigation. And that brings us to that step 4, and we're transitioning into this phase of the project currently. And the aim is to get out and verify and quantify our desk-based work. So where we have identified a recommended area, just to get out and actually see how much water is there. And Darren will detail in his work, or sorry, in his talk after this about what exactly goes into that type of field work. But we're aiming to get out and investigate some of the larger data gaps that we've identified, such as quantifying aquifer properties, investigating surface water and groundwater interaction where appropriate, or if there is any, and testing the groundwater chemistry also. And the overall aim is to guide sustainable supplies which will meet the requirements of the new legislation. Funnily enough, simultaneous to the development of this recommended area in the D, this is a sliver of regionally important karstified aquifer. There were 2 boreholes installed in the area near Drumcondrath, and they got terrific results. They hit a megaliter a day, and not only that, but of water of potable, very high quality. So the site acted as a bit of a proof of concept for what we're doing in Groundwater 3D, and is an example of the potential that these recommended areas might hold. Again, Darren will talk in a bit more detail in his presentation about what goes into a site-specific assessment as it might have been carried out at this site here in Drumcondrath, up in Meath, I should have mentioned. So just to very quickly summarize, the Groundwater 3D catchment, our project is a catchment-based assessment of groundwater resources. It is a 4-step approach where we firstly identify potential groundwater resources. We scrutinize those areas for potential limitations in the abstractions within those zones. We compile all of that together to make a list which we can prioritize and use that to inform where best to focus our field work to verify and quantify resources. And we're currently transitioning into this step at the minute. So thank you for listening. I'll hand you back over to Ela now, and we'll address any questions at the end. Thank you very much.
Thank you very much, Joe. That was very interesting. And now we can move on to our next speaker, Darren. If you could share your presentation, please.
Okay, so you can see that okay? Right, so thanks for that, Joe, and thanks, Ella. So yeah, hello everyone. My name is Darren Clark, and alongside Corn Kelly of TOBIN Engineers, I've been working as a hydrogeologist on the National Water Resources Plan for the last 2 years. Taking up the work initially started in 2017. As part of this lecture series, Miriam Grant and Des Joyce of Irish Water spoke last week on the function and structure of the plan, as well as the medium to long-term strategic water outcomes associated with it. For this talk, I'll be focusing on the groundwater aspect of the project and the methodology used to assess groundwater feasibility. I guess it could be looked on as a natural progression from Joe's talk on catchment resource assessment. This will be taking a more site-specific look at the appropriate solutions to meeting the deficits. I guess just as a way to introduce, groundwater resources are important to Irish water. They provide upwards of 17% of total supply by volume. For the purposes of this framework plan, simple methodology is being developed for assessing the hydrological yield of the groundwater sites. I'll be bringing you through a couple of case studies to help explain the methodology, which takes into account a number of factors from risk to contamination, flooding, Aquifer Classification, and the concept of recharge and zones of contribution. As mentioned, the National Water Resources Plan's overarching objectives and strategic plan was covered in more detail by Miriam last week. Just for those who didn't catch it, here's just a brief summary. In order to secure water supplies into the future, Irish Water is developing Ireland's first National Water Resources Plan. It's a 25-year strategy for public water supply, where the needs are identified across all existing water supplies, resulting in plan level options being developed to address these needs. The plan will allow Irish Water to align its activities with EU and national policy, maintain services in changing natural and legislative environment, facilitate sustainable growth, economic development, and set clear approaches and targets, while also being transparent in its actions and activities. I thought it'd be useful then just to give firstly a brief overview of borehole construction guidelines. The design and completion of a borehole has a large influence on how the aquifer behaves in response to pumping, the associated drawdown, and the overall yield. These are important factors to consider when assessing existing sites and guidelines to follow when developing new groundwater supplies. The schematic here shows a typical water supply borehole sited in a bedrock which has a mixture of limited open fractures, and then a section with more connectivity where the fractures are more open at depth. This is often known as the reducing zone. Slightly different layout is this for sand and gravel aquifers, which have slotted well screens and a gravel pack in place in the place of the open hole section. These are currently much more common in the UK. So just to really the main features to consider is that for these kind of boreholes, you'd want a complete cement grout seal. The pump should be sitting within a PVC chamber casing. Both these will help to exclude the inflow of shallow groundwater. Furthermore, this will help to prevent large spikes in drawdown, which can have unwanted consequences, such as sediment influx and iron bacterial precipitate, as well as pump burnout. Lastly, the pump should be operating at a continuous stable rate. Conversely, then, if you look here at an example of I suppose, an older borehole design, which hasn't been drilled to the required spec. And what we would commonly see here is a lack of pump chamber casing or cement grout, inflow of water from both the shallow and the deep. You'll have the pump sitting at the bottom of the borehole. Motor can be sitting in the sand or clay. It's pumped intermittently and often exceeds the sustainable yield. You get rapid drawdown during pumping to a deep level just above the pump. Furthermore, you can get sand and clay being drawn in from the conduits whenever the pump is turned on. And oftentimes, a borehole like this, you'll see microbiology or turbidity issues. So something to avoid, really. And kind of the schematic then summarizes well what was discussed in the last two slides, while also illustrating the heterogeneity of Irish groundwater flow systems. So what we have, you can see this transition zone, which consists of a broken weathered zone lying at the top of the bedrock. This is widely recognized as a significant pathway for groundwater flow and potential movement of contaminants. The GSI are currently doing work to better understand its properties and extent at a national scale. And if we just switch to an older borehole design, we can see that without the necessary headworks and grouting, you're likely to get much more easily contaminated water coming in through the shallower system. And really in both these figures, we see the stratified nature of the shallow versus the deep groundwater flow system. A properly constructed borehole should just receive the inflows from depth rather than that contaminated surface flow. And then really the depth and the spatial extent of the drawdown from pumping is mostly a factor of borehole construction, pumping rate, and the properties of the aquifer itself. Although not directly related, I dealt with in detail here, a properly constructed borehole is imperative not only for providing a sustainable potable supply of water, but also helps reduce any potential impacts on say, a nearby sensitive habitat. This will be signified by a borehole that excludes surface water flows and ensuring a sustainable pumping rate, which would help to limit sort of fluctuations in the water table. And then I thought it would be useful just to kind of firstly define what yield is. It's a term that is used in the context of how much water can be extracted from a borehole. It normally refers to the normal abstraction possible in a 24-hour period. It's an important factor to highlight with regard to the National Water Resources Plan and to flag certain limitations at this stage of the project. Just a bit of background then, it's likely most, if not all, existing boreholes have undergone some form of testing and have also been in operation for some time. There are some reports available. However, in many cases, there's a lack of reliable information on the tests carried out. It was normal practice to simply see what sort of yield could be obtained from the borehole based on the driller's estimate of the yield, the anticipated abstraction rate, and the pump that was installed for the test. As such, a supply would have gone into production at around that anticipated yield figure. So, importantly, the yield depends on the aquifer, the borehole dimensions and configuration, pump size, setting, and efficiency. Once drilled, the aquifer and borehole are tested to determine certain hydraulic properties such as transitivity, permeability, and storage. The abstraction rate and drawdown are monitored, and the reliable long-term yield of the borehole is estimated from test observations. Over the course of the subsequent months and years, this may be modified in response to the established water level over the pump and the seasonal water levels. An established deployable output would have then stabilized. Over the next couple of slides then, I'll take you through two different sites both of which require a relatively small increase from the existing supply to meet the future demand. Abbey Fields, the preferred approach here was to augment the existing supply, which would require an increase of 46 cubic meters a day to meet the 2044 demand. And Davidstown then similarly augmenting the existing to meet a relatively small increase again. In the case of Abbey Fields, Hydro Environmental Services was commissioned by Atkins on behalf of Irish Water and Meath County Council to supervise the drilling and testing of a new trial well in the vicinity of the site. This provides useful information on the groundwater potential in the area, especially considering relative lack of information on the existing 4 boreholes. With Davidstown, then we're limited to an extent just with this sort of baseline information, which consists of a desk-based COC that was delineated by TOBIN in 2019, and just the registered abstraction rate. So taking a closer look at Abbey Fields, a camera survey of the existing boreholes indicated a number of issues which led to reduced performance and thereby yield. These included shallow completion depths and iron or bacterial precipitate which is clogging the screens. Although not of this particular site, the camera survey image here gives a good sense of the kind of conditions one would expect down a borehole. You can just note here the iron staining here on the sides. So with Abbey Fields, following the pump tests of the new trial well, a sustainable rate of 600 cubic meters a day was, potentially possible. This resulted in a drawdown of just over a meter at the end of the test, as shown by the pump test graph here on the right. Recovery in the well following the conclusion of the test was within 8 hours. I guess it's also worth pointing out that this test was completed during a significant dry period, so it likely represents worst case scenario aquifer conditions. Just on the sort of baseline conditions of this site, the boreholes were abstracting predominantly from an oolitic limestone. This class is locally important, generally, and can generally be moderately productive. The water quality was generally good, although iron and manganese was present. This, likely geologically constrained, currently being treated, so likely not an issue considering the current supply is undergoing the same kind of treatment. So really we can see that site-specific data is paramount to defining the local groundwater potential. Ideally, this should then be refined further with long-term groundwater level monitoring and water quality sampling to ensure both the quantity and quality remain consistent. I'll be dealing sort of a bit finer detail in assessing groundwater feasibility and yield with Davidstown in the next slide. I guess firstly, I just wanted to briefly outline, and Joe touched on it obviously with the catchment characterizations, but the Aquifer Classification for Ireland and its current scheme and the role that plays in helping to assess groundwater option potential. So the GSI class mapped nine bedrock aquifer categories across the country. These general types can be considered as systems that have similar properties with a good indication of resource extent and risk. So going down sort of through by scale, really, regionally important bedrock aquifers often can serve as public water supplies. So you'll be looking at good to excellent yields there, and they generally have an area of greater than 25 kilometers squared. And going down into locally important bedrock, reducing it in terms of scale of supply, ideally servicing something like a local public water supply or group scheme. Then into your poor bedrock aquifers, these are smaller again, can service more, domestic supplies or small group schemes. And then in addition to these bedrock aquifers, sand and gravel aquifers can provide a valuable resource subject to the permeability and thickness of the deposit. They can be subdivided based on aerial extent, generally classified as either regionally important if they're greater than 10 kilometers squared, or locally important if less than this. So aquifer and regional well yields can give a sense of yield or an option volume estimate for a new groundwater option. They often serve as high-level estimates and can be refined further at project level with site-specific data and trial well drilling and testing. Groundwater potential then is assessed from historical data on wells and boreholes, and it's used in the hydrogeological categorization of aquifers, informing potential for abstraction. I guess just to note that, like the variable existing information on some of Irish water supplies, the potential for large variations in subsurface geology, even over short distances, can make it difficult to produce robust desktop assessments of groundwater availability. So I guess Abbey Fields involved a scenario whereby groundwater feasibility and or yield for both the existing site and a new site nearby could be assessed. Looking at Davidstown then, we'll further outline the high-level desk-based approach to assessing groundwater potential. Some of the criteria used include aquifer designation, vulnerability, risk to flooding, and if available, water quality. And it's important to cover this just to put our assessments into the context. I guess what you see here with the Aquifer Map on the left, it shows the bedrock composed of Ordovician volcanics. These are then overlain by locally important sand and gravel aquifer, and this is what the borehole is sited in. The bedrock is classified as a moderately productive aquifer, local zones. These are often categorized by limited fracture and network connectivity, low fissure permeability, which tends to decrease with depth. They generally offer relatively low aquifer potential, although higher zones of permeability can occur at shallower depths where fractures can be more connected. When we look then at the map on the right, the vulnerability map, it's created based on a number of factors, including soil thickness, the ease or difficulty with which the soil transmits water to the water table. We can see here where the bedrock is close to the surface, groundwater is extremely vulnerable, and where the gravels are present, then the vulnerability is high, and that's really attributed to the fact that the gravels are derived from granite and are moderate to highly permeable or thin in places. And then really, so location, abstraction rate, and site configuration are often the minimum information available. As mentioned earlier, the current abstraction rate is useful as it's often related to that first primitive test. It's also the rate established over a period of time, which normally has not declined. Thus, there is a correlation between the existing abstraction rate and long-term yield. Ideally, yield estimates would be based on a 3D assessment of the geology within the vicinity of the supply, supplemented with long-term records of pumping and drawdown of levels over many years. Where there's little information, the zones of contribution can be used to assist in the desktop assessment of the yield. Just to really give a definition of a ZOC, broadly just defined as the area needed to support an abstraction from long-term groundwater recharge. Their delineation considers groundwater flow, recharge, and the area required to support the abstraction from long-term groundwater recharge. There are spatial approximations based on available information on the source and include interpretations of topography, geology, groundwater flow, vulnerability, and chemistry where available. So in the case here, we have a ZOC that has been, so the Davidstown ZOC has been defined or constrained using the topographic height to the north and the surrounding watercourses. Just looking at this recharge map, then we can see the higher rates of recharge are concentrated over the gravels, while the lower levels to the north consistent with the Ordovician volcanics and metasediments. So here the gravels are likely to receive significant rejected recharge from the steeper side of valleys, runoff and flow downhill, recharging the gravels, and to some extent, most likely the Slaney. So following this, a water balance can then be undertaken using the abstraction rate and the recharge. This provides us with an area needed to supply the yield and can be compared to the delineated SOC to see how much bigger or smaller that SOC area is than the area required by the water balance. And we use 150% of the current abstraction rate as a factor of safety to allow for potential to expand to meet future demand scenarios or critical dry weather periods. It's a high level approach which can give us an indication of whether the option can supply part or all of the deficit, or whether a new well may be required to be drilled nearby. I guess just to put into context the yield, reliability in particular, to highlight any issues and uncertainties around the ZOC. For instance, the ZOC can be much larger than the abstraction, than the current abstraction, which could suggest that the potential yield or the current yield is safe and sustainable. But this could be misleading, as for instance, and touched on in those first few slides, borehole configuration can be constrained and can in fact limit any production. Furthermore, insufficient information may have been available to define a more appropriate ZOC at the time. On the other hand, a ZOC may be much smaller than the current abstraction. That is, essentially the area alone cannot provide sufficient replenishment of a groundwater abstraction. In many of these instances, the zonal contribution cannot increase and additional flows cannot be captured, which oftentimes leads to reduction in the yield of the well. On the other hand, the borehole, could lie next to a river. And it's actually the river there that's providing much of the recharge. In our case with Davidstown, the ZOC here was delineated at 0.6 kilometers squared in area. And this was deemed to be big enough to support the normal abstraction plus a 50% factor of safety. It was, deemed to be 3.5 times greater than the required area to meet the increase in the abstraction. And I guess just to note here at the bottom, the caveat is that this site represents a simplified assessment, and it hasn't undergone the more detailed approach that some of the more well-developed public water supplies have undergone, such as that of Portlaoise. A simplified assessment to delineate ZOCs has been applied to many of the smaller sources, and the hope would be to then target specific sites to study in more detail based on source size or local issues. Really bringing us to the summary then. This is a flow chart here to help just summarize the methodology that we've used in our groundwater feasibility assessments. And again, just making use of GSI's groundwater vulnerability mapping and the work done for the groundwater flood project to sort of assess the risk to contamination and flooding. As mentioned, the Aquifer Classification scheme playing an important role, giving us an indication of resource extent and risk. Moving on then through the process, assessing the abstraction rate with the recharge and the ZOC to allow us to get us to a water balance and really giving us a high level indication of the options potential. Again, yeah, the importance of proper yield assessments and ongoing pump test assessments. And then really just to summarize, aquifer and regional well yields give a sense of yield and option volume estimates for new groundwater options. The quality of the data is variable, ranging from high quality reliable, such as the Portlaoise, and to relatively limited poor quality data. Where there's information, we can use the ZOC to assist us in a desktop assessment of the yield. Critically, site-specific information is used. The NWRP process takes into account these site-specific information where available. The yield is based on the known abstraction rate, which is governed by a number of factors, including borehole construction configuration. As further assessments are made and relevant data collected, iterative improvements will be made to this. And lastly, then the GSI are undertaking catchment scale water resource assessments, including cumulative impact estimates. Irish Water plan to collaborate with GSI and utilize the results of these to inform future decision making. I guess similarly, this applies to the work Joe presented on with the GSI flagging sites of potential groundwater resource development, and the ultimate goal then to further develop these at project level. So that's it really. And I think there's time for Q&A. So I'll hand it over to Ella, I think. So thanks for listening.